Okay, so hi everyone. My name is Ishan, and I'll be presenting this paper called Benchmarking the Robustness of Deep Neural Networks to Common Corruptions in Digital Pathology. This was written by Zhang, Sun, and some other authors, and they're from Zhejiang and Westlake University. So first, some context on the problem. So the robustness of any diagnostic model for any clinical application with respect to image corruption is crucial. Especially deep neural networks, they're further susceptible to corruptions for two main reasons. One being that complex image processing involves tasks like tissue processing, cutting, staining, scanning, storing different types of tissues, muscles, and then eventually converting those to images. And the other reason is that there's interclass differences between images, and they can be blurry or hard to interpret, especially if the images aren't clear. And it can be hard to identify decision boundaries. And so predictions made by diagnostic systems need to be robust. Otherwise, there's some serious problems because we make influential decisions based off of the predictions, like for treatment decisions or for whatever, I guess, the classification task is. And so the problem statement is they want to build a model evaluation criteria for to evaluate whether a deep learning model is, I guess, robust. And so the challenge is that it's sort of infeasible to have a model that tests every type of corruption. And so the goal of this paper is to develop a easy to use benchmark that evaluates some deep neural network to the most common cases of corrupted pathology images. And specifically, they have 9 types of common corruptions that occur most commonly in pathology images. And for each type of corruption, they allow it to take on 5 different levels of severity. And then they define metrics that allow them to better evaluate the stability of any prediction from a model. And so some related works have been done. The paper cites works not necessarily in medical imaging, but they do talk about how deep neural networks are vulnerable to different types of corruption, especially blur and Gaussian noise. And as in digital pathology specifically, there have been problems with bubbles and uneven illuminations. And prior deep neural network studies were made in the context of image recognition and further extended to object detection, semantic segmentation, person re-ID, and pose estimations. And so this paper is inspired by prior improvements, but it's specifically designed for pathology images with regards to specific corruption types and predefined metric choices. And they define a new evaluation metric to define the stability confidence under corruption. And they cite unreliable confidence as a major weakness of most deep neural networks. And so now we'll talk about the design of the benchmark. So a typical, I guess, classifier would be like the one you see up here, right? So you have some classifier F trained on a sample distribution D, and you're basically checking if the prediction matches the expected value. But when you're training this classifier with low quality images or corrupted inputs, it's not as suitable. So they define the classifier such where they have some C of X, which is a corruption function, as an input to the classifier, and then they check if it's equal to the expected value. And C denotes the set of corruption functions that they study, and I'll talk about that later in more detail. And they also define, I guess, a benchmark for the confidence ranking under corruptions. And so intuitively it makes sense that corruptions will undermine the confidence of any classifier. And so it should be expected that with these poor samples, the prediction should be less confident. And so we want the confidence estimation to match human intuition. And so typically for some given input, you want to see with how much certainty can you say that it will make some prediction. So it basically defines a prediction or a confidence, I guess, sort of benchmark that says if you have two corruption samples, S1, or on the same input with severity level S1 and S2. And let's say that S2 is a more severe corruption than S1, then we should be more confident about S1 than S2 because intuitively a more severe corruption should not be more confidently classified than one that's lower. And so in this case, C of x0 would just be the clean original image because 0 would mean that there's no severity. And yeah, severity ranges from 0 to 5. And 5 is the most severe, 0 is just the original. And so now let's talk a little bit more about the different types of corruptions that this paper uses. So this paper uses JPEG corruption. This is basically a loss, or I guess a lossy image compression format, and it's supposed to imitate the image distortion by different storage formats. These are some of the formats that you will see with lossy compression that were used in this study. And another one that was used was pixelation. Pixelation occurs when maybe you enlarge an image beyond the true resolution, and then maybe you train data on, say, 40x magnification, and you test it at data that's 20x magnification. You will have some difference in, I guess, image quality just because of pixelation. And zoom, especially, can be a big factor. And then they talk about something called defocus blur, which basically is when the focusing accuracy or the autofocus is out of sync. There's also a similar type called motion blur, which means when you take a sample or there's some difference in camera exposure, there can be some blur just because of, I guess, the environment, or maybe it was shaky. And then the next one is brightness, saturation, and hue. These are pretty self-explanatory. And then mark, they define mark as any stain being used by a pathologist marking an image with some sort of pen. And there's also a bubble corruption, which happens when you let air get underneath the cover slip of some test sample. And so this table basically summarizes all the corruptions and the types. So JPEG and pixelation are digitization type of corruptions. We have blur corruptions, color corruptions, and these two are stain corruptions. And so this is just an image of what each of the, I guess, corruptions look like. These are the two data sets that they use. One is called Patch Chameleon and the other is called Local TCT. The top left image in both of these is the original, and you'll see how each image looks under a different corruption. The defocus is the hardest to interpret, and you can see for motion, it looks a little bit shaky in both of these. And it's pretty obvious here there's some sort of bubble that's forming, and you can see how brightness, saturation, and hue are also affecting the image quality to some degree. And so each corruption type, like I mentioned, comes at 5 different severity levels. S0 is the original, and S5 represents the most severe. And so it goes from least severe to most severe, and pathologists reduce the confidence from left to right because the severity of the image has gotten worse. So it'll obviously get more difficult to classify. But interestingly, in this example, the prediction confidence actually goes up, which is actually a problem because you shouldn't be able to classify more corrupt images with higher certainty than less corrupt images. So that's something that the authors recognized, and they come up with a separate metric for that, which I will also get to. And so the first metric that they defined is just corruption error. This basically is an aggregation of all the corruptions at different severity levels. BCS basically denotes a corruption type C, that's severity S. And you basically you aggregate them and you divide it by the number of corruptions and severity levels. So in this case, it would be 45 because there's 9 different types of corruptions and 5 levels of severity for each one. And this is, I guess we represent this with CE, corruption error of the prediction. The second metric they define is to represent the degree to the degraded performance resulted from corruption. they simply define this as CE, which is on the previous slide, over the error on the validation set without any corruption. And this is corruption error of confidence. This is basically a measure of mismatch between the pathologist's intuition of the confidence values and the classifier predicted confidence rankings of the corruption images. And so V denotes the validation set, and S of X is basically a rank of the confidence sequence of, say, a given prediction at some at a specific corruption, right? So X sub 0 all the way to X sub n sub S, which represents the most severe, and that sequence is then compared. Oops, that sequence is then compared with the intuition of confidence with that of a pathologist, and they use the Kendall tau as a way to compare, I guess, the association, which is basically a coefficient of similarity between the two rankings. And they divide that by the comparison time between any two confidence values of S. And it actually works out to actually be, if you were to have a bubble sort and you were to reorder them, it would just be the count of the number of swaps in the bubble sort. That is kind of how Kendall tau works. But you then take the sum of all of the images in the validation set and again divide it by 1 over NV times NC to get the corruption error of confidence. And so now getting to the experimentation side, they use two different data sets like you saw before. One is a histopathological data set and one is a cytological data set. The patch chameleon data set has this many sample, or I guess this many training images and this many validation images, and it's at 96 by 96 resolution. The local TCT data set, this one has slightly less training set and roughly the same validation and test set. And this one is actually a 224 by 224 resolution. And one of the problems with, I guess, the decreased resolution of the patch chameleon dataset is that for testing it on the transformers for their DNN selection, they weren't able to do that because the training procedure was unstable for that set of data. So for the choice of deep neural networks, they chose 10 CNNs and 3 vision transformers that are listed here. And these are the 10 CNNs that they decided to compare using each of the metrics I mentioned before. And these are 3 of, I guess, the most common vision transformers that they decided to use for this experiment. And so now we can dive into the results of their experiment. So the first thing to observe is it's pretty clear that image corruption decreases the prediction value just by looking at the RCE. Just in case you forgot, RCE defines the relative degradation of performance compared to the original clean data. And if you look at both of these columns, you'll see values are actually ranging from 1.8 all the way to 2.8. And values that are underlined in bold represent the best results. Values that are just bolded represent the second best results. And so if you just look at the RCE columns, you'll see that they're pretty high. And that basically means that the corrupted images are almost 0.8 to 1 times 8 times larger in terms of misclassifications, which tells us that these deep neural networks are not very robust to changes in corruption. So that's our first observation. The second observation you can see is on both datasets, AlexNet has the worst error. Here on the patch chameleon, it has 14.94, and on the local TCT, it has 16.06. But interestingly, the RCE value is actually the best amongst all of them, which means that the relative degradation of the performance, or I guess measure of robustness, was actually better, even though it had the worst performance. And although CNNs have improved their performance over the past decade, on corrupted images, the performance change is very little. As you can see at the CE values, they're all pretty high and they're very similar. And It's an interesting take because you would think that over time CNNs would become more robust to uh, high variance in input, but this, I guess, this metric shows that that may not necessarily be the case. And if you then compare the three vision transformers to the rest of the CNNs, you'll see that the three vision transformers actually have smaller RCE values, showing that they're slightly more robust than the others, which I guess sort of makes sense because some properties of vision transformers allow them to be more robust, like the self-attention mechanism, which allows for, I guess, more information about the global input space rather than just the localized area that maybe a CNN will get. And you'll also notice that model confidence is unstable to image corruptions by observing the CEC value. Remember, that's a measure of the mismatch in confidence between the observed, or I guess the confidence of the prediction and the confidence of a pathologist. We see that the values, again, they are all pretty high. They're ranked from 35% to 55%, which means almost half of the confidence values are falsely ranked. And this also shows that the confidence estimations of modern CNNs are pretty poor. And if you just compare the CEC values of CNNs and vision transformers, we notice again that we notice that the confidence of vision transformers is actually less reliable than most CNNs, which I found quite interesting. And there wasn't actually much explanation of this, so I was hoping maybe I could discuss with Dr. Chen after, but I found this to be very interesting. And even more interesting, I noticed, was that the CEC and RCE seem to be in opposite directions, meaning that if a model had better robustness of the prediction, its robustness of confidence tended to be worse. Meaning, if you look at AlexNet, it has a pretty good RCE value, but its confidence is pretty bad compared to, say, if you look at the ResNet for the local TCT dataset, you'll see it has an RCE of 2.24, but it has much lower CEC. And remember, CEC is the degree of mismatch, not confidence. So lower CEC is actually desirable. This is a continuation of the results. So this first graph you'll see is the patch chameleon validation set and the error on the test set. It basically shows a correlation between the predictive abilities of the validation on the test set. And it has decent predictive ability, but patch chameleon C, which is the corrupted benchmark, actually has better correlation with the test set results, 0.37 versus 0.51. And that result is more magnified actually in local TCT, where the original validation set actually has very poor predictive ability on the test set. It's almost negative, but with their proposed benchmark, it's much, much higher. So to further continue discussing the results, a given architecture may be more robust to certain types of corruptions while more vulnerable to others. It was briefly mentioned, for example, AlexNet, the performance varies slightly when encountered with JPEG images. Maybe the loss will be like 21%, but for different types of image corruptions, maybe like Q, it will be severely impacted to something like 38.5%. And a possible reason for this is that AlexNet is sensitive to statistical variation while robust to texture detail. This study, or I guess this paper, doesn't really do a good job, I think, of going deep into the individual corruptions. It does more of a aggregated study. So it's kind of hard to pinpoint why some, I guess, models are more robust to some certain types of corruptions than others. And it's very clear that the corruption type has an effect on the performance. Most architectures, they had a CE value below 20% on mark corruption, but for others may have had a 30%, above 30% on defocus blur, showing that on some it may act one way, but it may not necessarily hold true for another type. And for the performance of the models, especially the mismatch metric, there's a large variance in terms of corruption. So one model may have a mismatch of say 48%, but for another one it may be as high as 72%. Again, showing that different types of corruptions play different roles in the deep neural networks. And it was also shown that early stopping helped to improve robustness, which makes sense because regularization has been used to prevent overfitting, which is useful for model robustness. And in the study, it was found that overfitting was actually harmful to corruption robustness, which intuitively I think makes sense. And so, as a conclusion, a variety of deep neural network models suffer from significant accuracy decreases and have unreliable confidence estimations on different types of corruptions. In some cases, the error was almost double on the corrupted data set. And the proposed benchmark showed that it's more reliable than the validation set, accurately evaluating the generalization behavior of the model. Or more accurately evaluating the generalization. And that was shown in this graph right here, where it compares the validation set to the benchmark. And so the contributions of this paper were the two classification and ranking metrics that are designed to evaluate the stability of the prediction and the confidence. And the benchmark had 45 different types of corruptions, 9 individual corruptions with 5 levels of severity each. And it proved to be a better indicator of test performance than validation set, as I mentioned. And the benchmark also speaks about the generalization ability of the model, as shown with the Pearson coefficient graph. So some of the strengths of this paper, I thought the paper did a good job of evaluating DNNs because they picked 10 different types of CNNs and 3 different types of vision transformers. And I think if you're able to test it on a wide variety of CNNs and vision transformers, I think it speaks more to the generalizability of the benchmark as a whole. And the code is also linked in the abstract as a reference. So people that wanted to maybe replicate or verify the results were able to do so. And I thought the corruption setup was also well thought out because it covers 45 types of corruptions and severities, and they picked 9 that they thought were the most common in digital pathology. And the CEC metric I thought was very clever, especially using the Kendall-Tau for mismatch comparisons between the observed and the confidence rankings of the people that were of the experts rather. And I thought it exploited the severity ordering well for the ordinal rank comparison. Some weaknesses of the paper, I thought that there wasn't very much insight onto why vision transformers had worse confidence of robustness compared to CNNs. And an ablation study would have been nice to differentiate what type of corruptions affect different CNNs and how. They kind of, again, grouped all the corruptions into one metric and just said that, okay, either this model is good at generalizing or it's not. And I also wish they had some data augmentation techniques involved in the study because it is being used more commonly for especially for data sets that are high in variance. And so it's a little surprising that they didn't consider data augmentation in testing for robustness. And it's kind of hard to judge the effectiveness of the benchmark without comparisons to other state-of-the-art benchmarks. It purely relies on the validation set as the baseline. And for future directions, I think it would make sense to try the study again, using data augmentation and different strategies to help mitigate high variance. And testing on different types of corruptions would also be useful, aside from the ones that were in this paper, so that you could identify any patterns in specific types of corruptions and which corruptions may make training harder for some models compared to others. And testing the corruption benchmark on different problems, I think, would also be useful to see if the benchmark is effective at tasks like segmentation. This one only did classification, so we might see different results on different tasks. On the NIPS review scale, I'd give this paper 2. I think it was a good paper, and I think it did a thorough job of investigating the different types of corruptions. I thought a little bit of the conclusions were a bit abrupt and hard to follow, especially when they relate to generalizability. And there was some insight again lacking on what model robustness techniques, such as data augmentation, would have on the benchmark. And I guess it's left as a future direction in the paper as well. But I think the benchmark does an impressive job, especially with the CEC metric using Kendall Tau. And I thought that was pretty noble. That's perfect. Yeah, and that concludes my presentation.